Hello, I'm Michael O'Connell, and in tonight's video, we're going to be deriving an expression that relates the height of a ball in a rotameter to the volumetric flow rate. So, when we analyze this problem, we have to realize that the ball inside this rotameter must have zero net force acting on it. The acceleration has to be zero. We have to be at steady state to determine what the volumetric flow rate is related to the height of the ball, of course. So, that means that we can do what most of us have probably done in physics classes, where we draw a force body diagram. Okay, so let's take our ball to be just this dot here. Okay, so what forces are acting on it? Obviously, we have the weight of the ball. The ball is going to be more dense than the fluid. That way, we can actually get a measurement. If it wasn't, the ball would just float to the top, and it wouldn't give us any indication of the volumetric flow rate. So then we have some upward buoyant force, because this ball is fully immersed in whatever fluid is flowing upward through it. Okay? So this we could call F sub B, and then this is F sub G. Okay? But this can't work, right? We're not done because these aren't equal. So what do we have? Well, we have flow, of course. We have the fluid that's flowing upward through here. Okay? Now, obviously, because we have this little ball in this very, very small tube, we're really only concerned about the forces that are acting in the vertical direction, of course. So we're going to have two forces that need to balance here, right? Because we have fluid below the ball and fluid above the ball. So we have two pressure forces, okay? We know that pressure forces act normal to a surface. Specifically, we need what that overall pressure force is normal to some surface. So how would we do that here? Because we have this, basically, if we draw a better sphere here, we have some hemisphere, right? Okay, and we have forces from the fluid acting on the ball, okay? So it looks like we might have to do some nasty integration, but what we can do instead, actually, is realize that these perpendicular components of the force are actually all going to sum together, such that if we just choose a cross-sectional area within this sphere, within the ball, that is perpendicular to the pressure force that we want to find, that is the area that we can use to find that pressure force, okay? And this might sound familiar because we did the same thing back when we found pressure forces on that barrel of fluid. If you recall, we had a barrel horizontal like this. And when we were interested in finding the force on the curved side of the barrel, so coming out of the page at us, we actually just took, okay, of course based on the height of the fluid, we just took a rectangle, right? Because we know that all of the force that's exerted on that curved side had to come from somewhere. Well, it came back here in this middle rectangular cross-section. So we can use that for our area. Now, of course, that was a little bit different, right? Because we had this constant length, of course, but we did have to differentiate small changes in height, okay? But in this case, we just have that cross-sectional area, okay? So that's this horizontal cross-sectional area into the page through the ball there, okay? Now, that's super great for us because, as I said, if that's our cross-sectional area, so we could just draw it like a line like that, okay? That's inside the ball. What does that mean for us? Well, that's good because we're concerned with the forces in the vertical direction. So we have a pressure force from 3, okay, acting downward, right, because it's acting against the object, against the flow. And then we have the pressure force at 1. So we have F sub 1, F sub 3. Okay, and these need to balance, of course. And of course, this is going to be greater, right, because it's pushing it up to some steady state such that there's no acceleration, okay? What's great is that these forces, of course, you have to pick this cross-section because this cross-section is perpendicular to our pressure forces, okay? So hopefully that makes sense. And if it doesn't, you can always watch the video I did on pressure forces within a cylindrical barrel because I may have explained it a lot better there. Okay, so what does that mean for us? I would always hate this about free body diagrams if you have more than like two forces, but as I said, so you would have like F sub 3 coming down, and then F sub 1 coming up. And then if you were doing this on your physics test, you would say, oh wait, not that. You would say acceleration is equal to 0 in the y direction or something like that. Okay, so our force is balanced. So let's describe those forces. So remember those four forces. So we know gravity, right? That is quite easy. That's just the mass of our ball inside the rotameter multiplied by the acceleration due to gravity. For our purposes here, we'll describe that in terms of the volume of the ball, actually. And why are we going to do that? Well, we also know that we want to describe the buoyant force. The buoyant force is equal to the weight of the fluid displaced by the object. Okay? So, of course, what's displaced is the same. That's going to be the volume of the ball. This rho sub F, that's the density of the fluid that's flowing through. Okay? Because again, it's the weight of the fluid displaced that's the buoyant force. Okay? So, it serves us well to express F sub G, the gravitational force on the ball, as rho sub B this time, of course, because it's the density of the ball. And this would, of course, be multiplied by the volume of the ball, V sub B, and the gravitational constant there. Okay? So, those subtract. Now, we know that the gravitational force is greater, so we can write this on one side of the equation. So, what would we have here? We have some difference in the densities, of course, and then Vg. And this is, I should specify that this is V sub B, just so that we're clear that it's the volume of the ball. Okay, equal to, that would be F sub 1 minus F sub 3. What is F sub 3? Okay, here we just have to ask ourselves, okay, well, this is obviously acting on some cross-section, okay? And we're given, in the way I drew this, we have a diameter of our ball. So that's what we're going to want to use here. That sometimes throws people, including myself, for a loop sometimes, because your expression for the cross-sectional area here is pi d squared over 4, so not pi r squared. So you have that expression there. That's your area, and then, of course, your pressure force P sub 1. Okay? And this, of course, conveniently, is the same for F sub 3, right? So what would our right-hand side of the equation look like? Well, we would just factor that out. So you would have P sub 1 minus P sub 3 is pi d squared over 4. That is a wacky pi right there. Okay. Oh, one thing I forgot to address, of course. We can maybe get some cancellation here since we're given the diameter. The volume of the ball, this is an even more weird expression, but this is going to be pi, the diameter cubed over 6, okay? So that's the volume of the ball, okay? So let's see what cancellations we would get if we substitute that into here. So, again, that was pi d cubed over 6. And then, of course, the gravitational constant. Okay, so these expressions are equal, so these cancel. They have to be equal, again, because the acceleration is 0. So we have a d over there, the pi's cancel, okay? And multiply both sides by 4. You would get some 2/3 there. So you'd have 2/3. Again, the pi is gone. dg, and then rho sub b minus rho sub f, okay, equal to the pressure difference. This leads perfectly into the next thing I want to talk about. This is a new concept. It's extremely important, though, when we're dealing with these types of problems, okay, in which you have fluid flowing through a certain area. Now, we are going to be talking about fluids that are incompressible such that the density is constant, which you probably gathered, because if I'm using all these densities, I'd probably, or specifically the density of the fluid, I would have mentioned if it is going to be changing with respect to some other variable or variables. So what we want to analyze here is we want to get the velocity of the flow. Why do we want to do that? Well, ultimately, we can describe the area here at 2, the area here at 1, area at 3, whatever it is. Obviously, we're going to need this large d, the diameter of our tube in this problem. And of course, the whole point of this is to relate the volumetric flow rate of our fluid to some h, right? Some height along this tube. So keep that in mind. We're going to need those here. Okay. What can we say about the pressure at 1, the pressure at 2, and the pressure at position 3? Okay, so from the continuity equation, we know that we decrease our area, right? So the flow of the fluid, right? The volumetric flow rate is conserved. So Q is equal to A, oh, that's a really bad A sub 2 times V sub 2, which is equal to A sub 1, V sub 2, or sub 1. Okay. So if we decrease our area, the velocity of our fluid goes up, okay? So we lose pressure, we gain kinetic energy. That's Bernoulli's equation. We're going to ignore the height differences between points 1 and 2. And also, to avoid other complications with solving this problem, we'll ignore frictional heating because these rotometers will be calibrated, okay? And we're just trying to derive an empirical relationship here. So it is okay that we don't consider that for this problem. So what we would say here is that when the fluid exits, what's going to happen? Well, you may see, oh, well, duh, it goes back to a larger area. But that's actually not the concept we're going to be applying here. So what happens to the fluid as it moves from position 2 to position 3 is a sudden expansion. So in a sudden expansion, there's no pressure recovery. What do I mean by pressure recovery? Obviously, when you have a constricted area, your flow is higher. Okay, so if we gradually increase, let's say, the area, the flow slows down, right? So we lose kinetic energy, right? So V goes down. And then pressure, of course, will go up. Now, that doesn't happen when we do a sudden expansion, which probably makes sense, right? So if I redrew that and we went through the same thing, but it was like really sudden, like we really just got a ton of area, well, wouldn't you say, and you could see this like intuitively, that the pressure here, right there, we could call that position 1, is basically going to be the same at the second point here, right? You're not going to gain that pressure back. There's not going to be any pressure recovery, okay, because the expansion is sudden. What does that mean for us in this problem? And why can we say it's sudden, right? You might be like, well, Michael, the way you've drawn it here, you have the ball and the sphere, and it doesn't seem that sudden. I mean, you have obviously the curve of the sphere and then the tube, but you get to that area again of the tube, at least the flow does, right? So it doesn't seem that sudden. But that's really not the case, because I've drawn this to show you where position 2 is, but the ball in here, it's going to be really tight, especially like at the bottom here. You don't want it to fall out, so it's literally going to be the diameter of the ball, at least at the bottom for sure, right? So there's not a lot of space here. There's really not. Okay, so basically what I'm trying to tell you is that A sub 2 is much, much, much smaller than A sub 1. That'll be important later as well. Okay? We also need to realize that the ball is extremely small. Okay? You have this very, very small radius. And basically, once you've surpassed that radius, once the flow, let's say you start at one point and the flow has reached, it's traveled upward, that radius, you've expanded a lot of area if A sub 2 is so much smaller than A sub 1, which of course is the same area up there at position 3. You've expanded a lot of area by traveling a very, very small distance. So what does that mean? The expansion happens very suddenly. Okay, so with the sudden expansion concept that I talked about here, what does that mean for the pressure at position 2 and the pressure at position 3? Of course it means they're equal, right? So P sub 2 equals P sub 3. And this is extremely important for us, because what we can do is substitute P sub 2 into here. Now, again, we are trying to relate the height of the ball to the volumetric flow rate of our fluid. That's what we're after. And I just said that we need these pressures to give us velocity, which we're going to use the Bernoulli's equation. Okay? So that is going to be our key here. And again, because these velocities are going to allow us to determine the flow rate. Okay? But keep in mind, we'll need the height as well. So how are we going to do this? I'm going to take the time to erase some things first. Okay, so I think we're ready to continue. So here is our pressure difference, right, in Bernoulli's equation. This is the frictional heating term, so we're ignoring that, as I said before. And then the small change in altitude there, or height, we can also ignore, because again, if you've ever seen a rotameter, they're pretty tiny. That's not going to have a big effect on the flow rate here that we're going to be trying to determine. Okay, as I said before, incompressible fluid, so we can use the continuity equation. So with that expression, we can find an expression for V sub 1. So V sub 1 is going to be equal to A sub 2 Sorry, I thought I was going to sneeze. That was kind of weird. This expression goes into there. Okay? And this side obviously is going to be 0. Because we have P sub 1 minus P sub 2, we can move that term to the other side. So once again, I'm going to erase some things here. Another thing I forgot to mention, when we're dealing with Bernoulli's equation, we have to consider the density of the fluid, if that wasn't already apparent. But I should be denoting that with rho sub F, just to make that clear. Okay, let's see what we can do here. Well, we're after this velocity. I should clarify, why are we after this velocity? We're after that velocity because at this point, right, we can use the radii. We can use the radius of our ball and, of course, the radius of our tube. And we can actually find the area of that very, very small gap. Okay, so that would allow us to find the flow rate, so that is important. Okay, but again, we still need to be considering, like, how is the height going to factor into this? Okay, which I will get to soon. So we have a V sub 2 squared over 2 and the V sub 2 squared over 2. So that factors out. Okay. And let's see how that might look. So we're going to have 1 minus A sub 2 over A sub 1. Now keep in mind this is still squared. Okay? Now what do we want to do with this? Now this term is annoying, right? Because we know A sub 2 is really, really small, especially with respect to A sub 1, as I talked about before, when I kind of redrew the smaller version of the tube and the ball and just said that basically the ball has to fit very, very nicely in this tube, and there's a very, very small area here, even though I've drawn it a lot larger. So what does that mean? Well, that means this ratio is very small, very, very small. And if we square it, it's just going to get smaller. Okay? So we're going to take this to be 0. It's approximately 0, which is great because then we have V sub 2 squared over 2 multiplied by 1. Okay? So that allows us to multiply both sides by 2 and then take the square root. And there we have an expression for the velocity at position 2. Okay? So that's going to look just like that. Excellent. So now, hopefully you see, because I actually have it circled still, we have P sub 1 minus P sub 2. I meant to draw that as a 2 there, okay? So this is equal to this, so we can plug this expression into there. Notice that we would have these 2's in the numerator under a radical, so we can pull that out, okay? So we can have a kind of a larger, maybe a little bit more obnoxious expression for the velocity at position 2. But basically, the good thing about this part is really you just have to be careful with your transfer, as you always have to be careful when you rewrite these things, right? This is what we get there, okay? This, of course, is to the 1/2 power. So this is a great expression. So basically, what does this velocity at position 2 tell us? This tells us that, hey, this is the velocity that you need to have such that this ball inside this rotameter is at steady state. Okay, that's important. There's one issue with that, though. What's the issue? We need height. Okay? The whole point of this video is we're trying to relate the volumetric flow rate, which, by the way, we could get, right? I said before, with the diameter of this tube as well, you can get this small gap area. It's really small. You multiply it against your large velocity flowing right through there, and you have Q. But again, similarly, so this Q of A sub 2 V sub 2 times V sub 2, this is only in that case, right, where the force is balanced, okay? So if we had some flow here that's larger, well, that's not going to work, right? Your ball is just going to shoot up, okay? And you're going to be like, well, shoot, I didn't relate this to the height. There's no h in this expression. And likewise, if it's less, then your forces aren't going to balance. It's going to drop right down. Okay, so we need a relationship for the height. Okay, now how is this going to work, right? Because we just have this fixed diameter. Okay, so that's a problem for us because basically, again, as I said, if you had a larger or smaller Q, the ball would go flying up. Why does it do that? Well, basically, it has no opportunity to reach steady state. Okay. Because again, we've just defined what this velocity would need to be such that those forces balance, okay? And then we just have this gap area. So something needs to change here, right? And this is why we use a tapered tube. And if you've looked at rotometers before very, 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 very closely, you might have seen it. It's not big, but by tapered, I mean like this, okay? Now, for the purposes of our equation, what does that allow? How does that actually work, right? So obviously we're interested in the height, of course. Okay. Now here, this is interesting because we have some diameter of our tube now, but it's changing. It's changing with respect to the height. As we increase the height, we're increasing our diameter. Why are we doing that? Well, again, you have that fixed velocity expression. That's helpful. What this allows us to do is, so let's say we have a larger flow rate. Well, what this allows us to do is this area increases, okay, as obviously as the ball rises, so your flow rate's higher, such that this ball, the ball in our rotometer, reaches steady state at some height that we can measure. Isn't that amazing? I thought that was really, really cool when I was taught this. So, okay, let's think about what would happen here. What do we have to describe? Well, as I said before, if we're concerned with Q, which we are because we want to relate this to height, we need an area. We need this. Okay? So what I want you to do is think if you had the rotometer in your hand and you look down it, right? This tube is a cylinder, and then you have a sphere. Okay? Now obviously again there's that small gap area here at position 2 that we're concerned with. So this would be your view, right? Actually, that's way wrong proportions. Okay, very, very small area. So we know that we have some diameter, lowercase d, and then some diameter, I'll just draw it like that. This is uppercase d. Okay, so we're concerned with area, so we would have that pi over 4, and then obviously the larger d squared. Okay, so that's that. That's helpful. Okay. There's one other thing we need, right? One other thing. The only issue with this expression is there's one thing that's changing, right? And this is important because this is what helps us. This is what allows us to solve this problem. This diameter of our tube is changing, right? Because we said it's tapered. Okay? It's changing with what? It's changing with the height. How do we relate that? Let's first consider what the diameter here at the bottom would need to be. I actually already said this earlier in the video. So we have the ball inside our rotometer. We don't want it to fall out, okay? So this at the bottom, to keep it there, this is lowercase d, right? This is the diameter of your ball, okay? So it doesn't fall out. But of course we increase that. By what? Well, notice the way I've drawn this. This is a straight line. Okay? Now what does that mean? You can almost think of it. You have height, diameter. It's like a graph, isn't it? In fact, you could even do a little axis, right? Get out some graph paper and graph it. Right? What quadrant is that? It's the third quadrant, okay? So that's really cool. What do we need to do here? We need to relate this diameter Okay, that's the diameter of our tube to the height. How do we do that? Well, it's just a slope, right? It's just the slope that we've created for this rotometer. Pretend we're designing it, right? Okay, so that's going to be some proportionality. So every time, so let's write an expression for the diameter, right? So what's our y? What would our y-intercept be like right down here? Like we would start at d, right? And then it increases by some slope, okay? M. The increase in this diameter, again, as we rise, as we increase h, if we, obviously this is positive direction, this is positive direction. Okay, that's why this is positive. Notice that? Again, kind of back to the coordinates. I know it's a little weird because I did it that way, but think of it this way. Yeah, your diameter would be increasing out. Okay, so as this term increases, the height is higher there. Okay, and that proportionality is completely based on the slope here, which we're going to call m. Okay, for our rotometer. This is great, right? Because now this proportionality, this is constant, right? Because this slope, well, that's just based on how we made this little rotometer with our ball inside. Now, this height here, that does vary, but that's the whole point, right? The whole point of this expression is to relate the change in height for the ball when we push, have fluid flow through this thing to the volumetric flow rate, right? Now this is the diameter of our ball, which is of course constant. So this expression here goes into the d squared. And if you would give me a moment, I'm going to be erasing some things. Okay, now we have an expression for how the diameter of our tube actually changes, okay, because it's tapered. So that was d, the diameter of our ball, plus mh. So that would be squared minus d squared. Okay, and then we can just do the algebra here. So this would be 2dmh. And we have somebody here. Hi. It's my mom, okay, and she wants to go to bed, and I don't blame her because it's a weeknight. You can come in. It's not a big deal. And here we would have m squared to h squared minus d squared. So these cancel. Now, what about this expression, right? Now, if you look up rotometers online, this m, the slope, okay, of our tapered rotometer, this is really, 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 really small. Okay, once again, these are very, very small if you've seen them. Okay, so we're going to approximate that, again, as 0, just as we did with the ratios of area 2, the ratio of area 2 to area 1. So this is 0, okay? So then we're just left with this term here, okay? And then, of course, that's multiplied by pi over 4. Now, what was this expression? This expression was for the area. So the second area is multiplied by v sub 2, because that was the area at position 2. So we have the flow rate, Q is equal to A sub 2 times v sub 2. Now, this expression, let me be careful here. So pi over 4 times this expression here, again. So this is pi over 2. Okay, notice the 2 would be on top there, so that cancels dmh. And then we have that expression there. So notice I factored the 2 out of the radical, so those actually go away. Then we have dg, the density of the ball minus the density of the fluid, over 3 times over the density of the fluid there. Okay? So that is basically going to be the answer. So I'm going to take the time to erase this so that you can see the final answer. But this expression, and I'm going to show you kind of a nice way to write this so that you get a nice expression that relates the volumetric flow rate to the height of the ball in the rotometer. Okay? So let's see what we could do with this, right? Well, we have dg up front, okay? And notice that you have 2 d's there, so this would be d squared, I believe. That might be wrong. I'll have to check that. And, oh, sorry, that is not correct because that's this is in a radical. Okay, so I forgot to draw that, but we have this expression here. Okay, so my last few comments as we wrap up this video, this is your final answer. This expression here is basically all determinable, right? These are constants, right? We have like the diameter of the ball, the slope of the rotameter that we designed, gravitational constant, density of the ball, density of the fluid going through. So all of those are things that we can find out, right? So now we have this expression, this very simple expression. You could call this like sigma or something, that relates the flow rate to the height, and now you can actually design a rotameter. So thank you so much for watching. Sorry about this stuff with the end of this video, and I hope you were still able to follow along and see everything well on the whiteboard. So I will see you next time.